Hi everyone, Senan this side, and in this video we are going to see this insertion sort algorithm. Fine, and this algorithm is a bit difficult to understand if it is your very first time, because there are certain assumptions that you do while solving this. So rather than taking a concrete example or maybe an abstract example, I would take a concrete example. So what you do is, given an array of elements and you are at currently this position, what you do is you assume this is already sorted and this part of the array is unsorted, right? And let's say you find an element x at this position. Now since this array is sorted, what you do is you place this x at its correct position, right? You push or you swap elements consecutive elements till the time you found the correct position of x. And after you've done that, your updated sorted array would be this, and your unsorted array would be the remaining part. So that is the logic. If it is not clear, let's look at an example. Let's take an array of elements 1 2 3 4 5 6. Okay, let's initialize some elements. Let's say 70, 10, 20, minus 15, 14, let's say 37. Now since we had to divide this in a sorted portion, let's say sorted and unsorted, right? So you assume that the sorted portion is, this is the sorted portion and this is the unsorted portion. Why? Because an array of single element is always sorted, right? So what you do is you take an iterator, let's say I, and what you do is, so let me draw this line. Okay, now you find, since this is sorted, you find the correct position for this 10. So you see, is 10 less than 70, right? So you perform a swap. So let's just do the swapping. Copy, paste, and what I do is I'll just say this is 10 and this is 70. Now if you see, this array is, let's write this as with this pen, right? So assume that the pink portion is the sorted portion and the yellow portion is the unsorted portion. Okay, so you see this. So if you observe, now this is the sorted portion, this is the unsorted portion. Okay, now I take this line and I make a line here. Now I would take this I, place it here, and see where can I place this 20 in this sorted array. So the remaining array, the initial part of the array is still sorted. So 20 is less than 70, right? So I perform a swap. So if I do that, let's create a copy, paste. Okay, so I compare this with 70, and if you see, if I place 20 here and place 70 here, we are done, right? But what I do is check, is 20 less than 10? No, that is false. So I just stop here because I know 20 is at its correct position. So what I do is I take this line, I move this line one step ahead. I'll take this I and place it here. Now in this iteration you would actually see what is happening. So I'll just make the updates in this array itself. So is 15 less than 70? That is true. So what I would do is perform a swap. So this would be minus 15 and this would be 70. Now what I do is I compare these two elements. Is minus 15 less than 20? That is true. So what I do is perform a swap. Again, so this is minus 15 and this would be 20. Now again I compare these two elements. Is minus 15 less than 10? That is true. Then so I would perform a swap. So in the end minus 15 would be here and 10 would go here. Now if you see, there are no elements behind this, right? So we are done. And again, if you observe, now we have this as a sorted array, this as an unsorted array. So I'll just take this, make a copy, paste this and move this line one step ahead and take this I and place it here. Now I do the same thing. I check is 14 less than 70? Yes. Then we perform a swap. So the swap would go like this. This is 14. This is 70. Again, I compare these two elements and they are not in the correct order. So we perform a swap. So 14 goes here and 20 goes here. Again, we compare these two elements. They are not in, or they are in correct order, right? So we don't do anything. So they are in its correct position. We don't perform a swap. So let's just change the color to this. Fine. So we have this as a sorted array, this as an unsorted array. Now I take this whole array, make a copy, paste, and what I do is I take this line and place it here, and so the I goes here. Now I take this 37 and compare these two elements. So are they in this correct order? No, that is false. So we swap these elements. So this is 37 and this would be 70. Now I would compare these two elements. Is 37 less than 20? No, they are already in the correct order. So we stop. So in the end, if you see, we have our array sorted using this algorithm. Okay, so how do we write the function or the pseudocode? So let's say function insertion sort. Right. So we have a sorted part and an unsorted part. So this would take array as an input. Obviously we need n, which is array size, and we need a for loop, right? So where does our I start and where does it go till? Okay, so I started from, assume 0, 1, 2, 3, 4, 5. I started from the first index and went till the last position in the array. So for I is equal to 1 and it goes to n minus 1, 0 based indexing. Fine. And what we do is we do a check, right? If till the time they are in correct order, we perform till the time they are in the incorrect order, we do a swap. So let's initialize j as what? J as I, and I'll say while j is greater than equal to 0 or greater than equal to 1, right? And I say if array of j is less than array of j minus 1, right? We are comparing the adjacent elements. So if this is true, what we do is we perform a swap of array j and array j minus 1, and after this I do is j minus minus or is equal to j minus 1, right? So we are comparing consecutive elements going from the right to the left. After we are done with this, if for some reason we are not able to find this, that means our j is at its correct position. So I'll say else what you do is just break this, right? Now why is j is greater than equal to 1? Because we are comparing j with j minus 1. So if j minus 1 is less than 0, then we are not searching a valid address. So that means j minus 1 should be greater than equal to 0. J minus 1 should be greater than equal to 0. So j is greater than equal to 1. That is how I arrived at this while loop. And yep, I think we are done. And in the end, we just return the array. Now this is the pseudocode. You can write this in any language you want to. Okay, now let's discuss the time and space complexity. Time complexity. So for every n, you are searching the previous part of the array. So for I equal to 1, we are doing one comparison. For I equal to 2, we are doing two comparisons. In the worst case, right? I equal to 3, we are doing three comparisons. Let's just look. When I is equal to 1, we did only one comparison. For I equal to 2, we had to check two comparisons. For I equal to 3, we had to do three comparisons. Although we won't always be reaching till the end, but assuming the worst case, this comparison would be done 3 times, right? For I equal to 4, you do one comparison, two comparison, three comparison, and four comparison in the worst case. For I is equal to 5, one comparison, two comparison, three comparison, four comparison, and five comparison. So that is the logic. And how long does the I go to? I goes to I equal to n minus 1. That means n minus 1 comparisons. Now you sum these elements, right? 1 plus 2 plus 3 dot 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 n minus 1. This is what? N times n minus 1 by 2. That means the complexity is of order n square. Big O of n square, order of n square, or quadratic order, whatever you want to say it. Now what is the best case? This is the worst case, right? What can be the best case? Assume your array is already sorted 1, 2, 3, 4, 5 and 6. Let's say you have to sort these elements. You go here, you don't do any comparisons. You go here, I is equal to 1. You do a single comparison, they are in the correct order, you break out of the loop. I goes to 3, you compare these two elements, they are in the correct order, you break the loop. I goes here, you are in the correct order, so 4 and 3 are in the correct order, so we break the loop. I goes here, you check 4 and 5, they are in the correct order, you move one step ahead. You check 5 and 6, they are in the correct order, and you finish. So for every n, you are doing a single check or comparison. So in the best case, that would be order n. That would be the best case. Assuming either the array is sorted or array is almost sorted, you would have some sort of complexity near about big O of n, right? But in the general case, this would be big O of n square. Considering the space complexity, apart from the array that is already given, you're not using extra space. So this is the space complexity would be constant, assuming you are not considering the array itself as a space. Okay, so that was the video, guys. Hope you understood something. If yes, be sure to share it with someone you think this might be useful to. And yeah, thanks for watching. I'll see you in the next video about merge sort.